All right, so last time we talked about how to name alkynes. We introduced what an alkyne is with a triple bond. So then we talked about how to name them. In other words, we name them the same way we did with alkenes. We're going to number it in the way that gets us to the triple bond the fastest. We talked about what happens if we have more than one triple bond: diines, triines, tetraines, pentaines. We talked about what happens if you have a double bond and a triple bond, eneines. And at the end of the day, there's not a lot going on with naming of alkynes because the geometry around a triple bond is linear, so we don't really have to worry about any stereochemistry. All right, and then so in that what we want to get in today is really start to talk about the reactions. And so the first thing that I'm going to do is I'm going to review the reactions that I did in the introduction. I'm just going to write them down. I'm not going to spend a lot of time doing them. And then we're going to jump in with the chemistry of alkynes a little bit more in-depthly. So let's go ahead and get that going. Let me switch over to my whiteboard. All right, and so one of the things that I said was that alkyne chemistry is very similar to alkene chemistry, and that certainly is true. And so there were a few reactions that I talked about in the introduction video that are very similar and essentially just don't change in any way when it comes to from alkenes to alkynes. And so the first reaction was a triple bond with HX. And if you do one equivalent, then you still get Markovnikov. And so let me add an R group so we can see that regioselectivity. We get an try it one more time. We get Markovnikov addition of HX. So that's really nothing different. If we take the same reaction, and this is what one of the other students was asking, this is one EQ, one equivalent. So that means one stoichiometric equivalent. But if we take this and do XS, and XS will be the symbol for more than I need, XS, then you simply get the addition of that X group twice. And so once you have the alkene, of course, it can then go along and react with HX again, and you can form the dihalide. So there's nothing really, I thought nothing essentially new going on with that. Same thing went with the addition of X2. So if you take X2 and you did one equivalent of X2, then you still get that that guy, and it's still, let me draw it correctly. So it looks like this. It's still anti-addition. But if I then take this same reaction and add excess X2, then I'm going to add X's everywhere. Every carbon gets an X. And so at the end of the day, it's, again, the alkene is able to react again just in the same way that it did before. So instead of reacting once, the alkyne reacts twice if there's enough reagent. Now, the last one, or the last one that is essentially exactly the same, was if we did excess H2 in metal catalyst, then we fully reduced the alkyne. Now, I'm going to draw this intermediate just to point out that all that's going on here is that we're reducing the alkyne to an alkene. We can't isolate this thing. And this is going to continue to react because it's actually more reactive than the alkyne. And you end up with a fully reduced alkane. So again, there's really nothing going on with that that's new. If you have hydrogen, you need excess, or at the very least, we could have said 2 equivalents, right? Because we need one equivalent per each pi bond. And so I have 2 pi bonds here. So I'd need 2 equivalents. We're going to get a full reduction in this metal with a platinum or metal catalyst. So this hydrogenation reaction goes along just the same as it did before. The other thing is then the only other reactions that I actually introduced that I'm not going to spend a whole lot of time talking about was, well, if I can't isolate this double bond, what if I want the double bond? Because once you have a double bond, right, then you can do lots of chemistry. Because you know all of the reactions of double bonds. And so there were 2 important reactions that I introduced that are essentially new in chapter 9, but they're not so new that I wanted to then spend a whole bunch of time talking about them in this particular section. And so it involved, well, what kind of catalyst do I need in order to actually isolate the alkene instead of getting all the way to the alkane? And it was this idea of a poisoned catalyst. And there were 2 poisoned catalyst reactions that we talked about. One of them got you a alkene, and the other one got you the cis alkene. And so we'll talk about the cis alkene first. So if I have an R group, a triple bond, and I react it with H2, and the catalyst is called Lindlar's catalyst, then that gets you a cis alkane. It adds the hydrogens exactly the same way as it did before, with them being adsorbed onto the surface of this Lindlar's of a metal catalyst, and Lindlar helps you make that reaction stop at the alkene. So this is a new reaction, but essentially what is the same is that we see H2 as a reactant. And so that should still tell you that at the end of the day, you're going to reduce the alkyne, but in the presence of a poisoned catalyst, you only reduce it to an alkene. The second one got you a trans alkene. The situation here is that it doesn't involve H2 in the reactants, and so it's not as easy to remember what the reagent is doing. But what we do introduce in this case is the idea that or what's similar is that we have a metal. And we should start to get our heads around the idea that metals reduce organic compounds. And this is exactly what's going to happen here, is that this sodium acts as a reducing agent. And so it's going to reduce the alkyne. So let me actually add another R group here. Let me add another R group here. This one gets you cis, and this one gets you trans. You still reduce the alkyne, you reduce it only to an alkene, you end up with a trans alkene. And so these are the reactions that I wanted to discuss that were very, very similar to the reactions that we have done before. The only 2 that are new are these 2 guys with this is called the dissolving metal reaction with the sodium and the ammonia. And the other one is H2 and Lindlar's catalyst. But essentially at the end of the day, you're still reducing the alkyne to an alkene. Anybody have any questions they want to shout out about that one? Type it in chat or raise your hand. I'll give you a beat to do that. Okay, so let's get into this chemistry though. And alkynes produce an interesting bit of chemistry, because if you remember, when we talked about all the way back in chapter 3, when we talked about different acids and different bases, we talked about the strengths, the relative strengths of alkanes, alkynes, and alkenes and alkynes when it comes to acid strength. We talked about the pKa here being on the order of 50, the pKa here being on the order of 44. So that's 6 orders of magnitude more acidic. But by the time we get out here, the pKa is 25. And so now we're all of a sudden we're something like 20 orders of magnitude more acidic than an alkene. 25 orders of magnitude more acidic than an alkane. So essentially, in that comparison, these two are essentially the same when it comes to acidity, and this one is way more acidic. And what that means is that there actually are reagents that can remove this proton. And so one of the things that we talked about in chapter 3 was this idea of what is a suitable reagent. And so we did a couple of practice problems in chapter 3 where we took a look at the idea, well, is hydroxide, is that a suitable reagent to deprotonate an alkyne? And so what we did was we wrote this acid-base equilibrium down, and we identified the acid and the base and their respective conjugates. This is an alkynide ion, ALKYN for alkyne. And then remember, negative ions in chemistry are often called ides. And so this is an alkynide ion. Consider the phrase oxide or alkoxide for a negatively charged oxygen atom attached to a carbon chain. So the question is hydroxide a suitable reagent to do this? And so what we did was we said, let's identify the acids. In this case, this is the acid, and in the other side, this is the conjugate acid of the base. So here are the two acids that we needed to compare, and that means we write down the pKa's. And so we say, look, what's the pKa here? And remembering that the pKa of or the equilibrium favors the side of the reaction with the weaker acid, and that the larger the pKa is, the weaker the acid is. And we'd say, okay, no, this reaction really favors the reactant side. It's really reactant favored. And so hydroxide isn't really a suitable base in order to deprotonate an alkyne. But there is another base called sodium amide, and the amide ion is the negatively charged conjugate base of ammonia. And so if you think about ammonia, NH3, it can function as both a base or an acid. It can gain a proton to become NH4 plus, but it can also lose a proton to become NH2 minus. And NH2 minus is amide or amide. There's that IDE again, amide ion, where this is ammonium. And this is, of course, ammonia. And so when ammonia becomes an even stronger base, when ammonia acts as an acid, now, ammonia is traditionally a base, so it doesn't like to act as an acid, but when it does, it forms a particularly strong base. And so let's think about how this would work. If I take sodium if something like sodium amide, mix it with an alkyne, then I would form ammonia plus the alkynide ion. And now I want to do this example. So this is still the acid. This is now the conjugate acid of the alkynide of the amide ion. And so I have a pKa here of still 25. But if you go back to your pKa chart and think about the pKa of ammonia, it's about 38. And so now all of a sudden ammonia is the weaker acid than the alkyne. And so in this case, this reaction really is product favored. And so if you take an alkyne, so the kind of the catch of this, the moral of this story is that if you take an alkyne and you react it with sodium amide, then you can form an alkynide ion with pretty decent yields. And if you can form an alkynide ion, what does this thing do? This is a nucleophile, and it does nucleophilic chemistry. And so one of the things that we're going to talk about in a second is that you can take this alkynide ion and you can react it with substrates that have good leaving groups, and you can form carbon-carbon bonds. And so think about it really, what I want to do is just take one brief moment and think about this from a synthetic point of view. If you have something like this with a terminal alkyne on it, then you can turn it into something that has a negative charge. And once you have that negative charge, then you can do something that that is familiar to you, where you react it with some other R group, and maybe that R group has a good leaving group attached to it. If it has a good leaving group attached to it, then it does typical SN2 reactions where you do a substitution, and now you can connect these two R groups. And then once you have these two R groups connected, maybe you can reduce this to a cis or trans alkene, and then all of a sudden you've got lots of different possibilities for what you can do with that reaction as far as synthetic practicality goes. And so we're going to introduce there's only going to be 2 reactions this semester that form carbon-carbon bonds, and this will be one of them. Once you've got this idea that you can form carbon-carbon bonds, then you really have expanded the possibility of all the different synthetic problems that you can get involved with. So we'll kind of get back to that here in just a second. Before we get going, though, I want to stop a beat and see if anybody has any questions. All right. So the first thing that I want to do then is to talk about what can I do to form alkynes. So if I want to form an alkyne, then I need to do how do I form an alkene? If I want to form an alkene, then I need to react something like this with a base to do an elimination reaction to form an alkene. Now, essentially what we're going to do is the exact same type of reaction, but what's going to change is the base. And for the same reasons that we just talked about when we discussed the acidity of alkynes, we're going to have to use a particularly strong base. But what we can do is we can use something, what we're going to have to do, though, is we're going to have to eliminate a leaving group twice. So in order to form an alkyne, I would need something that has 2 leaving groups on it, so that I can first form a vinyl halide and then do an elimination reaction again to form an alkyne. And so there's two options for this. The first option is just as I described it. I can have this guy with the two halogens attached at the same position. So that's certainly one of the options. The other option is that I can have the halogens attached here. So let me do some erasing real quick. I don't want to throw them into the reaction, but I want to say, look, here's option number one, here's option number two. In option number one, I would create this intermediate. In option number two, I would create that intermediate. But at the end of the day, both of these reagents, when you do another elimination reaction, would lead to the same product, this alkyne. And so if you take, so here are the two, while it seems like it's two reactions, it's really just one reaction. The reagents are exactly the same. We're going to use a really strong base, and it's the same base that we discussed before, sodium amide. It's 2 steps. It does need aqueous workup, and we'll think about that in just a second, why that is. But in either case, you're going to form the alkyne as the final product of the reaction. Now, why do we need aqueous workup? Well, it's just because we just described that sodium amide is sufficiently strong to produce a alkynide ion. So in step one, I'm going to go over here. At the end of step one, you actually end up with the alkynide ion. And so step two is a protonation step to make the alkyne neutral. And we already discussed that water it would be a strong enough acid to protonate an alkyne because of the differences in acid strength. And so that's something that we already know, or at least that part we already know. So here's 2 new reactions, or really it's 1 new reaction. It's the formation of an alkyne from a dihalide. And the dihalide could be where the halogen is attached at the same position or on adjacent carbons. So these are alkyl dihalides. All right, so the one with the halogens attached at the same position is called geminal. These are geminal dihalides, and this one is vicinal dihalide. But they're both, at the end of the day, dihalides. And they specifically have to be either attached to the same carbon or on adjacent carbons in order for this reaction to work. Now, if I had something like this, where I have a dihalide that has 2 R groups, then in this case, all I need is the sodium amide because it will do the elimination without forming an ion. And let me make sure that I put 2 equivalents here, 2 equivalents there. The reason I don't need the protonation step is that the acidity of alkynes only happens if there's a proton that's acidic. If I form an internal alkyne, there are no protons attached to it, so therefore it can't act as an acid. It has to be terminal in order to form an alkynide ion. And so that's going to be a synthetic consideration. You can't use an internal alkyne to form an alkynide ion and then add it to another carbon chain that has a good leaving group. Okay. All right, and so that's the really the only reaction that we need to know in order for us to think about how to produce alkynes. Then, as we start moving into the chapter, we start to talk about the reactions reducing alkynes with hydrogen. We talked about that one already. Reducing alkynes to form alkenes with poisoned catalysts. We talked about that already, whether it's Lindlar or the dissolving metal reaction, which is sodium metal and a liquid ammonia. We talked about then reacting alkynes with HX, whether it's one equivalent or in excess, whether we're going to form a vinyl halide or an alkane, or a halo, in other words, a geminal dihalide. We can form that from an alkyne. Then we talked about, there was one reaction that I didn't mention at the beginning in the review, and that's anti-Markovnikov addition of bromine, HBr, in the presence of peroxide. So let me do that now. You can do this same reaction that you did before, and you can get a mixture of products. This one is the major product. This one is the minor product. That's also a reaction that I discussed in the introduction that I didn't review at the beginning of this discussion, so my apologies. So we did talk about that one as well. Again, this is not a new reaction. This reaction is something that we've talked about before in alkene chemistry. It's the same reaction for alkynes. But instead of producing an alkane, it produces an alkene. So one of the things that I mentioned at the in that introductory video was that hydration of alkynes happens in a similar way as it does with alkenes. But there's a little bit more that is going on with that, and that's why we need to talk about it right now, because it's a little bit more in depth and it is something new. And so what I want to do first is write down the reaction. So it's a similar hydration in the fact that I'm going to use H2SO4. But there's a couple of different reagents that are involved. The new thing is this mercurial sulfate, and then some water as well. Now, what's similar to the reaction that these reagents show up in alkene chemistry is that we're going to do a Markovnikov hydration. We would typically add OH in the more substituted location. Now, this is not oxymercuration demercuration. This is acid catalyzed hydration. But and there isn't an analogous oxymercuration demercuration reaction for alkynes as there is for alkenes. But just like oxymercuration demercuration in alkenes and acid catalyzed hydration of alkenes, which are both Markovnikov additions of water, you have mercury and acid to remind you that of those two alkene reactions when it comes to an alkyne. We're essentially doing a Markovnikov addition of water. What's different is the product is not an alkene. The product is a ketone. There is an intermediate enol that forms that is perfectly analogous to the Markovnikov hydration. This enol rapidly tautomerizes, the word is tautomerize, and I'll spell that and define it here in a second, into the ketone. It's not exactly resonance. It's more of a, it's actually the movement of a hydrogen. Okay. And so what we want to do is we want to show you the mechanism that's involved with this transformation. And so it does involve this mercury catalyst. And so I want to go through it. And so what I want to do is I want to go back and I want to erase this part. Let me erase that part. And then I'm going to break out that mercurium sulfate just like this. All right, so now I can do my reaction. So the alkyne attacks the mercurium ion. That's the first step. And that's going to form a vinyl cation. Of course, since it forms a vinyl cation, the vinyl cation will form at the more substituted location. The vinyl cation is more stable than, vinyl cations are not stable in general, but of course the more substituted vinyl cation will be more stable than the least substituted vinyl cation. And then water comes along and attacks that location. And then another water that's in the solution comes along and deprotonates to form an intermediate, or to form what is almost an enol. Now with that acid that I just created, I'm going to form an intermediate that's resonance stabilized. And the resonance stability looks like this. Okay. And now reforming the double bond. This gets the intermediate enol and reforms the mercurium ion. Okay, so it is a new mechanism. It is something that I want you to know. It really isn't vastly different than what we've done before, but it is a different enough that it is going to take some practice to kind of get this one down. And so at the end of the day, you're going to form this enol, but remember that the enol isn't isolatable. And so at the end of the day, what we want to do is we want to take that enol and find out how does that enol transform into the ketone. And this is where this idea of tautomerization comes into play. So a tautomerer, so tautomerization, Tautomer, a tautomerer is a constitutional isomer formed by migration of one hydrogen. And so at the end of the day, what you'll see is this hydrogen essentially moves over to there. And so that's what we want to do with the mechanism that we're going to do it with. Now, the thing with tautomerization is that tautomerization happens in acidic conditions and it happens in basic conditions. Right now, what we're going to talk about is the acid catalyzed tautomerization of an enol to form a ketone under so this is acidic conditions. And so one thing about mechanisms where there's more than one possible way to do this, to do the same transformation, is that you have to think about the conditions of the reaction. One of the ways to help you remember how the mechanism works as you sort of work through it on a problem, a quiz, or an exam is to say to yourself, if I start with an acid, then an acid has a positive charge, and that means that I can't form any negative charges in the process, in the intermediate process. So if you think about how you start the reaction, in other words, the conditions, then you know that throughout the course of the mechanism, you can never create a negative charge because a negative charge can't exist in the presence of so many positively charged acid molecules. And so what you'll see in the course of this reaction is that everything in the middle of this particular mechanism involves positive charges. And so what we do is we take this acid and it protonates the double bond. That's the first thing to start with. And that forms in the intermediate a resonance stabilized cation. And you saw before how this can be resonance stabilized. The electrons on the OH group can form a protonated carbonyl group. And you can see the positive charge delocalize between the carbon and the oxygen. Now, once you've done that, you can have water come along to reform the catalyst by deprotonating that positively charged carbonyl group. And at the end of the day, that's what forms the ketone. So let me pause a beat and see if there's any questions about that. Okay. All right. So that was a new reaction, and that was the Markovnikov hydration of an alkyne. But just like we have a Markovnikov reaction of an alkyne that involved very similar reagents that we used with alkenes. So the question was, the OH doesn't leave. No, and so remember what we're talking about is the tautomerization of an enol to a ketone. So the OH doesn't leave, but the H does leave. And so it's one way to remember it is the full name of it is eno keto tautomerization, or excuse me, keto enol tautomerization. So this is actually an equilibrium that favors the ketone. All right, so just like we have the Markovnikov version, there's also an anti-Markovnikov hydration. So if you remember the anti-Markovnikov hydration of an alkene, it involved BH3 and THF. we're going to essentially use the exact same reaction here, but instead of BH3, the reagent changes just slightly to R2BH. The second step is still hydrogen peroxide and sodium hydroxide. Now, if you think about it, you would say, okay, this might produce the anti-Markovnikov hydration and form an enol that looks like this. But now at the end of the day, even though this is the intermediate, we're starting to have some idea that enols rapidly tautomerize, and what you end up with this in this case is an aldehyde. And so I don't want to show you the mechanism that involves the actual the intermediate parts, but what I want to do is I want to show you the tautomerization mechanism. And so before we do that, though, I just want to point out the reason that we use a more sterically hindered borane is that if we use BH3, then the alkene can then do successive additions with boron. And so we use a sterically hindered, back that up. We use a sterically hindered or dialkyl borane in order to prevent that second addition and stop and control the synthesis of the reaction. In other words, to stop the intermediate alkene from reacting further and leading to products that aren't useful. So that's why we use the R2. The R2 can be two different things. It can be 9BBN, which is a bicyclic borane compound. So at the end of the day, you can look up the structure. I don't want to draw it out. I don't want to draw it out right now, but you should think that this is also a borane. And then there's I can't even say the word. Looks like this. I'll let you guys pronounce it. Anyway, at the end of the day, what I'm going to show in all my reactions is R2BH. But you should become familiar with 9BBN because you want to. It is an alkyl borane and a dialkyl borane, and it's a common reagent that's used in organic chemistry too. So at the very least, kind of at least write that down in your notes so that you have some sort of muscle memory about it for organic chemistry too if you're going on there. At the end of the day, we're still going to form a ketone or an enol. And so what we want to talk about is how does this anti-Markovnikov enol transform into aldehyde with base instead of acid. And so if you notice, the conditions of this reaction are basic. And so you're going to do a tautomerization, but in this case, the tautomerization is base catalyzed instead of acid catalyzed. And so just like the consideration that you made with acid catalyzed tautomerization, you don't want to form an intermediate that involves a positive charge in this case. So if you're struggling through the mechanism and you're trying to figure it out, remember that anything that forms a positive charge is a no-no. And so you can think about how to struggle through mechanisms as you move forward in organic chemistry by remembering that the conditions of the reactions dictate the possible steps of the mechanism. In this mechanism, the conditions of the reaction are basic. So I can't form anything that's positively charged. I can form things that are neutral, but I can't form things that are positively charged. And what I'm going to do in this case is only form intermediates that are negatively charged. So the first thing is a proton transfer, forming a negative charge on that oxygen. This oxygen with a negative charge is now resonance stabilized. Where I can show the negative, in this case, it's the negative charge that's delocalized. In the acid catalyzed version, it was the positive charge that's delocalized. It's still shared between the carbon and the hydrogen. I created a water, and if it's a base catalyzed reaction, then I'm going to reform the catalyst. Hello. That negative charge reacts with the water. And that's what gets me my product and the reformed catalyst. And so let me pause a bit and see if there's any questions about that particular reaction and the associated tautomerization mechanism. All right, so just real quick to review. There are two hydration reactions that are similar, but they lead to different products because of the tautomerization. If I take an alkyne, I can do a Markovnikov hydration. It involves similar reagents, although the mechanism is just a little bit different. In this case, I form a ketone. I can do an anti-Markovnikov addition. In this case, it tautomerizes as well. These conditions are basic, but this way I form an aldehyde. And so the identity of the functional group can help you decide when you're doing synthesis which one of these reactions to use. If you want to form a ketone, you'd use the Markovnikov version of the hydration at the top. If you want to form an aldehyde, you'd use the anti-Markovnikov hydration at the bottom. Okay. All right, so the next one that I want to talk about involves oxidative cleavage. I did mention that briefly in the video for the introduction. It's also a similar reaction. Where you have O3, but instead of DMS in the second step, it's water. Now, what's similar is that the reagent is ozone and it's a two-step reaction. What's different is that the second step is water instead of DMS. What's similar is that I am going to completely break the carbon-carbon bond here. I am going to completely separate these two carbons. When it came to the alkene, I completely broke the carbon-carbon double bond, and I formed two products. One was that one, and the other one was this one, where I put a doubly bound oxygen where the double bond and the alkene was. Now, I'm essentially going to do the same thing. I am going to add a double bound oxygen to both of those carbons. What should help you remember the products of this reaction is that since I'm going to add a double bond oxygen to that carbon, but I do have an extra pi bond, and that extra pi bond can additionally react to continue the oxidative process. If I think about this carbon and this carbon, those two carbons have become oxidized. And if you think about the range of of oxidations for carbons, I can have a carbon that has no oxygen on it. I could have a carbon that has a single bond to an oxygen. I could have a carbon that has two bonds to an oxygen. And the very most oxidation that I could have for a carbon is one that has three bonds to an oxygen. And so in this case, in the case of the alkene, I got here. But if I have an alkyne, I have an extra pi bond, and I can do the oxidation even further. I end up with a carboxylic acid. So the reaction of this alkyne produces two products. I'm going to have an R group and that carbon that started the triple bond, and it's going to now be a carboxylic acid. The other product is this R group and that other carbon attached to the triple bond, and it is also a carboxylic acid. So it is new in the sense that it produces a completely different functional group as the product. It's the same in the sense that we are oxidizing the carbons that had the pi bonds, and we're completely separating those two carbons by doing oxidative cleavage. We're completely breaking the two carbons apart and oxidizing. So that's oxidative cleavage. Any questions about that? Let me stop a beat for that. Okay. If there's one last reaction, and we've already reviewed it to some extent. This is if we take an alkyne, and it has to be terminal, and we react it with sodium amide. We know that if we take an alkyne and it's terminal, and we react it with sodium amide, that amide is strong enough to form an alkynide ion. Once I've formed an alkynide ion, if I react it to a group that has a nice unhindered substrate and a very nice leaving group, then I can do an SN2 reaction. Let me make this R prime to form a new carbon-carbon bond. And so this is a new reaction. This is a new reaction for you. What's new about it is that we're going to apply an old mechanism, SN2, with a new nucleophile, an alkynide ion. So if I take an alkynide ion that has a good leaving group, I can do that old SN2 reaction and form a new carbon-carbon bond. So this is a really important synthetic reaction. And the reason that it's important is that it adds carbons to the carbon chain. At the end of the day, especially at the end of this semester, but totally, more importantly, at the beginning of Organic Chemistry 2 and throughout Organic Chemistry 2, your synthesis problems will invariably involve changing the number of carbons in the initial starting material. And so those reactions that allow you to either reduce or increase the number of carbons in a particular reagent are bottleneck reactions. If you have 75, 85, 100 reactions to choose from, but only 10 of them at the end of the day, at the end of Organic Chemistry 2, only 10 of them change the number of carbons in a carbon chain, then you know that you were limited to using one of those 10 reactions. You no longer have 100 to choose from, you only have 10 to choose from. And so this is the new reaction that I wanted to bring up right now and show you what's going on. And how we can use it in synthesis. We can even combine it more thoroughly if we think about ethyne. Ethyne has a terminal alkyne at both ends. We could do something like this. We could react it with sodium amide, and let's do methyl iodide. The product of that reaction would be to add a methyl group here. Then I can take this, react it again with sodium amide, because I still have a terminal alkyne, and let's react it with propyl iodide in this case. And now the product of this reaction is that thing. And once you have this longer carbon chain, you have all of the different possible reactions of alkynes that you could do with it, including the reactions that would change this into an alkene. And once you're able to change that into an alkene, you have all of the possible reactions of alkenes to choose from. And so using a terminal alkyne to form carbon-carbon bonds is a significant reaction in your synthesis problems, because it's a starting point to forming alkynes that you can then do all sorts of alkyne chemistry with, including forming alkenes. And once you've formed an alkene, you can do a lot more chemistry with that as well. So let me just stop right there with one quick beat to see if there's anybody that has any questions. All right, so let's do let me do a couple of quick examples. Because the last little thing that I want to do for this chapter will involve synthesis, and so we're getting to that part. So let's start off with some of that. Let's imagine that we want to take, this is ethyne, also called acetylene, and let's use acetylene to create this molecule. So what's the synthetic strategies? And so I want to use just, there's only going to be a couple, we only really need to form the carbon-carbon bonds. And so we're only going to use the reaction that we just discussed, which is the alkynide ion formation. And I think what's important about this particular reaction is to remember that when we do the alkynide ion to form, when we use alkynide ion to form carbon-carbon bonds, the triple bond stays intact. So that means that those green carbons are still right there. They're still right there in where that triple bond is. And so that means that we added the carbons on the left, and we added the carbons on the right. And so all we need to do is do the two synthesis reactions that add those carbons. And it doesn't matter which order that we do them in. So we could start off with the carbons on the left and say, I'm going to react sodium amide with how many carbons? I need 1, 2 carbons, and it needs to be attached to something that has a good leaving group. That forms that. And so that's the left half of the desired product. Now I can take that same product, react it with sodium amide again, and now I have to have the carbons that are on the right. So that means that I have this carbon, this carbon, this carbon, and this carbon, and it has to be attached to a good leaving group. So at the end of the day, I've added these carbons on the right and these carbons on the left. Stop real quick there and see if there's any questions. Any questions? All right, let's try a couple of other problems and then we'll wrap it up for the day. What other synthetic strategies can we do? All right. So I think we've already discussed this particular piece, which is remember that we can take a triple bond, we can turn it into a double bond by using a poisoned catalyst. Or we can take that and turn it into an alkane by using H2 and regular old platinum catalysts. Of course, we know how to take an alkene and turn it into an alkyne as well. So when you're, so the question was asked earlier, could you do it all at the same time? The answer to the question is no, because if you have R, you've attached the R group to it and you've formed an alkynide ion and you've got it all into a pot that has this and this in it, which one of these is it going to attack? It'll attack them all at the same time. So you'll end up with a mixture of products. You'll end up with this one, you'll end up with this one, and then you'll end up with your desired product. And so you can't have, so in order for there to be synthetic practicality, you can't do it all in one pot. You do have to do it in a series of reactions. So the question was asked about the previous example that we did. Could you do it all at the same time? And for synthetic practicality, you would need to list all these steps separately because you want to avoid the undesired side products. Any other questions? That took care of that one for you. Okay, so remember from a synthetic standpoint, we know how to take triple bonds. We can turn them into alkanes and we can turn them into alkenes. Also, we know how to make triple bonds. So let's say we start off with an alkane or an alkene. Is there a way that we can turn it into a triple bond? Well, this is an example of retrosynthetic analysis. If you're starting with an alkene and you want to form an alkyne, how do we form alkynes? What are the reactions that we know in order to form alkynes? Well, remember that it's going to be a reaction of sodium amide and water, and it's going to be from a geminal or a geminal dihalide, or I keep forgetting that other word, geminal, and I'm looking back at vicinal, a geminal or vicinal dihalide. And so we do know how to form this vicinal dihalide from the alkene because we know how to do the addition of Br2 to the alkene. Oh, sorry. And so this is another set of now how we're going to combine all of these reactions that we've learned in the last two chapters together in order to do some synthetic chemistry. And so let's just do a couple of more practice problems real quick. What if I had this guy and I want to create this guy? Okay, and so this is an example. So I'm going to try to use retrosynthesis exclusively solving these problems. And so maybe you're looking at this and you're already seeing how you can approach this in the forward direction. But as these problems become more complicated, I think it's better to approach them in the reverse direction. And so let's think about the product and how we could create that product. What is the product and what are its qualities? Well, the product is an alkene. It is a cis alkene. And at this point, if you think about it, you only know one reaction that makes cis alkenes. You can make a cis alkene from an alkyne Let me count my carbons, because if you're not counting carbons, you're not doing it right. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We can create a cis alkene from an alkyne if we use H2 and Lindlar's catalyst. So let's think about how, now that I've got the first step in the backwards direction, let's continue to go backwards. And remember, there is this little bit of faith in retrosynthesis that eventually at the end of the day, you're going to get to the reagent that you started with. So then let's take a look at this thing and let's see what it is and what its qualities are. Well, it's an alkyne. And remember, there isn't any stereochemistry to consider because the geometry is linear. Well, at this point, we're thinking about, well, how do we make alkynes? Well, I can make alkynes in several different ways. I can do elimination. Or I can do carbon-carbon bond formation. So let's just think about, and it's totally okay to think about all the different possibilities while you're working on these problems. But what would happen if I did elimination? Well, if I were going to do elimination, I would still have all 6 of the carbons, 1, 2, 3, 4, 5, 6, and I would have to have done it with a vicinal dihalide, and I would have to use something like sodium amide to do that. This reaction would certainly work. So there's nothing wrong with thinking that way. Let's think about how I could do it with carbon-carbon bond formation. Well, how would I do it with carbon-carbon bond formation? Well, I guess it doesn't really matter which way I look at it. I can start by thinking about those carbons, or it's what I'm trying to get at is I wanted to figure out which carbons am I adding. Remember that if we're going to do carbon-carbon bond formation, the triple bond already exists. Since this thing is symmetrical, it doesn't really matter which way I decide to do it. If I want to think about it in terms of the red ones came first, or I could think about it in terms of the purple ones were the ones that existed. Since it's symmetrical, it doesn't matter which way I think about it. Later on, it's really sort of half a dozen one way, 6 to the other, and it really does eventually just, it really is based on, well, what was the starting material? You know, does that lead to the starting material or not? And so in this case, since it's symmetrical, it will lead to the starting material. So if I were to react something with sodium amide, and then I want to add the 2 red carbons, so that means I had CH3, CH2, and then a good leaving group, I could do that reaction. Well, then what was there? What was there right before it was the 1, 2, 3, 4 purple carbons and that terminal alkyne. So there's 1, there's 2, there's 3, there's 4. Now, what about this alkyne? So now I've figured out how to make the carbon-carbon bond. Can I do this? Well, we don't know how to directly make alkynes from alkenes, so I'm going to need an extra step. But what do I do know? So I'm going to have to, I'm kind of getting tight here on my room, so I'm going to move it down here. I do know how to make this alkyne, and it's similar to this reaction that we talked about and haven't finished discussing down here at the bottom. I can do an elimination reaction. If I do sodium amide and I react 1, 2, 3, 4 carbons, and it was a vicinal dihalide, I can form that product. Now, since it's terminal, I'm going to need water to reprotonate it. Can I do this? What was right before that? Can I form the dihalide from the alkene? And the answer to that question is yes. So I've solved the synthesis. I've come up with one solution. And remember, there are multiple solutions most of the time. So if I were to put it all together in one single answer, I would say step 1, Br2. Step 2, sodium amide. Step 3, water. Step 4, sodium amide. Step 5, CH3, CH2I. Step 6, H2 Lindlar. Now, later on, as you become more sophisticated, you'll see that these 2 steps aren't actually necessary. But it's okay for any of my solutions to think about them in terms of the reactions that you learn. It's not necessary, because at the end of step 2, you are left with an alkynide ion, and that alkynide ion can react directly with the reagent in step 5. But I would not ever count off for you using water and then deprotonating it again with step 3 and step 4. I would never count off for that. So what I want to do is try to wrap it up, and let's see if there's a way, if I can figure out synthesis from that one. And so what I want to do is I'm going to have to do a little bit of erasing, get rid of that solution. Let's see if I can back this up. Well, how do I know this reaction? Well, I can do this reaction because I can add Br2 to an alkene. And so I could, and it wouldn't matter if it was cis or trans alkenes. Well, the question is how do I make alkenes? Well, I can make alkenes by doing an elimination. And I could eliminate this alkene. So that's 1, 2, 3, 4, 5, 6. And I would need only a Br in that location to do an elimination. The problem is once you get to this point, as you start to think about retrosynthesis, is once you get to this point. If you did elimination with a base, there's no way to control. Does it add to that side? Or does it add to this side? And the red one is what you want, and the blue one is what you don't want. And since there is no way to control it, this is what should kind of clue you in to stop thinking about this possible path. Because at the end of the day, the solutions to these problems will involve really obvious answers that don't put you into places where, well, I'm not really sure how to control it. If this is all you can think of, then that's certainly something that path you can go down and get some partial credit as far as an exam is concerned. But remember, the clue is that you can't control which direction that eliminates from. You get a mixture of products, and mixtures of products are synthetically impractical. And so that synthetic impracticality is what clues you into the fact that this alternative pathway is probably a pathway to stop thinking about. So once you've decided, if we went this way first, once we got that way, we would say, all right, this isn't the way to go. Let's start this one over. get back to this alkyne. And so it must not have been elimination to form the alkyne. It must have been carbon-carbon bond formation and go back down the original path, which got us to the right answer. Okay, let's do one more. Pause just a second, see if any other questions on that particular example. All right, let's try the same reagent. Let's produce a different product though. All right, so one of the things that you should be doing when you're doing synthesis problems is you should always be counting the carbons. In our previous example, when we were trying to form this product, it was obvious that there's more carbons. If we counted them up, eventually we added 2 carbons. And so we said, okay, 4 carbons, 6 carbons, we're going to have to do a carbon-carbon bond formation reaction at some point. And so that's going to eliminate some of these possibilities. At this point, on this particular reaction, we have 4 carbons in the reactant, and we've got 4 carbons in the product. So we don't need to do a carbon-carbon bond formation reaction. All we need to worry about is changes in the functional group. So let's think about it in that sense, and let's kind of work backwards again as well. So what do we know about this thing? It's an aldehyde. And that's the only thing we can identify about it. It's a 4-carbon aldehyde. So in other words, we've got a double bound oxygen and it's at the end position. So I know 2 different ways that we could have done that. We could have done ozonolysis. If I would have had those 4 carbons connected with the double bond, and it wouldn't have mattered what that R group was, I would have been able to break that bond and form the double bonded oxygen exactly where I want to. But there's something there that's telling me that maybe I shouldn't think about that reaction. What's telling me that I shouldn't think about that reaction is that I'm wasting all of this stuff. It's synthetically inefficient. The more carbons that I can maintain, the more efficient the synthesis is, and the more likely you are to be going down the correct pathway. So I'm going to eliminate this pathway right away, because I would have to waste whatever carbons were attached to that. Even if it was just 1 methyl group, that would be a waste. And so I don't want to think about that possibility. Yeah, and so the next consideration to make is that the only other way that I know how to make an aldehyde is by doing an anti-Markovnikov hydration of a 4-carbon terminal alkyne. I could do anti-Markovnikov, so that would involve R2BH, sodium hydroxide, and H2O2. Remember that there would be keto-enol tautomerization in this process, but the enol that would form anti-Markovnikov would then tautomerize into the aldehyde. So I know how to do that. So I'm okay with that. It's the same number of carbons. So let's think back this step. How do I make an alkyne? Well, we really only know 2 ways to make alkynes. We can do carbon-carbon bond formation, or we can do elimination. Now, we've already discussed synthetic practicality. We already have all 4 carbons that we need. So carbon-carbon bond formation may work, but it's not going to be synthetically practical, because we'll end up with, we already have all the carbons that we need. And so we're going to end up either using more carbons than we need to, or wasting some carbons somewhere along the line. And so I'm not going to think about carbon-carbon bond formation. I'm going to think about the other way that I know how to make alkynes, and that's through elimination. So I can do sodium amide and water, and then what would I have needed to eliminate? Well, a geminal or vicinal dihalide, and I do know how to typically make vicinal dihalides, so I would have 1, 2, 3, 4 carbons, and there would have been a bromine there and a bromine there. No problems. I can definitely do that reaction. Now that I've done that, I've still got my 4 carbons. I think to myself, how can I make a dihalide? Well, I can make a dihalide from an alkene. I can make a dihalide from an alkene by adding Br2 to it. I've gotten back to my starting material. So the synthesis solution would be listed as 1, Br2, 2, sodium amide, 3, water, 4, alkyl borane, 5, sodium hydroxide, hydrogen peroxide. That's the solution to this synthesis problem. And in this case, this is required. Okay, so I'm going to stop there. That's the end of chapter 9. We're completely done with it.